Okay, here are two more reactions for us. So when I look at my starting materials, I see that this O minus is probably going to be my base. I recognize O minus as one of my strong bases, but the thing that it's paired with is just a CH3, CH2, CH3. We don't recognize that in any way as being something that's acidic. However, when we look over at the products, we do see that somehow that CH3 on the end was deprotonated. We know that that's not something we would normally do, but let's just go through the motions really quick for this reaction so we can see what might happen. That's how we would get that if we treated this species as an acid, okay? And then the acid would become the conjugate base, and what was the base becomes the conjugate acid. And now if we look up the pKa's for these, we probably don't even have to do that because you know that this is going to be a very reactive conjugate base compared to the other one. But let's compare the acidity of this acid. If we look up the pKa of a CH3, we're in the realm of 49 for our pKa. And the pKa of an alcohol, such as this one, is going to be about 17 or so. Might even be a little less. But this is definitely not product favored because this is the stronger acid. This is definitely the stronger base. This is definitely the weaker base compared to CH or C minus. And this is definitely a weaker acid. We haven't even been considering CH3's acids so far, okay? But now we need to look which way the equilibrium will lie. This is definitely going to be reactant favored. So much so that I don't even know that this would react in the forward direction. Okay, a tiny bit might. So we would draw an equilibrium arrow like that. Now let's draw our energy diagram. Okay, if this is reactant favored, the reactants need to sit lower in energy than the products. So this is going to be in reverse. Reactants need to be lower and the products need to be higher. And we'll draw our curve between them that looks like this. So let's fill in our reactants. This is our products. Activation energy. The activation energy is, if we're going in the forward direction, is the amount of energy it takes to go from reactants to products. So this is our activation energy in this case. This is at the top is our transition state. And then when we look at the change in energy between reactants and products, we're going to say, well, since the reactants to the products, that is going to be endothermic, a positive delta H. Okay, so there's our energy diagram, and notice that it looks backwards from other ones in a lot of ways. Okay, so at this point, I would expect that looking up the pKa's, determining the acid base, conjugate base, would be pretty much a review. So let's take a second, pause, and label all that information to get ourselves ready to do our energy diagram, okay? Okay, I took the time to label my base, acid, conjugate base, drew some mechanistic arrows to prove to myself the direction that the electrons would move to do this mechanism. And then I went to look up the pKa's. So I looked at the pKa of the acid, of that alcohol group, and I saw that it was 17. And I went to look up the pKa of the conjugate acid, and since it's also an alcohol, I would also be expecting it to be in the area about 17 for a pKa, but it's not going to be exactly 17 because there's a fluorine on that compound and there's not a fluorine on the other acid. And so we need to compare the pKa's of these two alcohols, even though they're the same functional group and structurally pretty similar, but there is going to be some differences. How do I know if the pKa of our conjugate acid is going to be more than 17 or less than 17? Let's look at the stability of the conjugate bases. So that is still a useful thing to do. I'm going to look at my base first over here on the left-hand side. I see a minus charge that it can be stabilized via induction because of this fluorine on that base. I look at my conjugate base on the right-hand side, and I don't see any fluorine or any kind of induction stabilization. So taking that into account, I'm going to say that the base, this is the more stable, weaker base. Okay, and we know that the more stable, weaker base corresponds to a stronger acid. So when I'm thinking about what the pKa for my strong acid will be, it needs to be smaller than 17. So I'm going to say it's probably about maybe 16, maybe 15 to 16 or so, but it needs to be lower than 17 because the conjugate acid is more acidic than the acid because the base from which it came is more stable than the other base because of induction. Our base is more stable than our conjugate base because of induction. All right, so if that's going to be the case, that our the stronger acid in our more reactive conjugate base is on the right-hand side, the product side, then our weaker side is actually the reactants. So we're going to draw reactant arrows or the equilibrium arrows that show that this is going to be reactant favored. And then I need to make sure I represent that somehow in my energy diagram. If it's reactant favored, then the reactants will sit lower in energy than the products. So I will draw something that looks like this. Here's our reactants. Here is our products. I'm going to identify the activation energy. The activation energy comes from the reactants up to that transition state. Okay. And then when we're looking at whether or not this is exothermic or endothermic, the overall change in delta H, we are looking at the distance between reactants and products. And because the reactants are lower than our products, it would be, I'm drawing that arrow in the wrong direction. We would actually need to show this way. This would be a positive delta H, making this endothermic. Okay. And so now when we think about whether this reaction would go forward in the forward direction, the answer is it probably would not, because the reactants are going to be more stable than the product. So the equilibrium would certainly lie towards the reactants. And if we think about if we made products, any products at all, the reaction would probably go in reverse. So there would be a lot of reversibility heading back in the other direction. And the reason for that is we can see that the activation energy from the products to our transition state, we have an activation energy in that direction too. That activation energy would be much lower. So this would probably be reversible, and we would see that the reverse reaction would be favored. The reverse reaction is favored is another way to say that something is reactant favored at equilibrium.